holiday greeting cards, one per person, and there might be a few extras left at the end. Our speaker tonight, who will be speaking, I'll give a short introduction prior to that, and our speaker tonight will be Dr. Christine Chen. I'll introduce you in a moment as we get through, and she will be talking about debris disks and the formation of young planetary systems. Upcoming public lecture series talks are January 3rd or 10th. I guess it's TBA. I think that's why Frank gave me these slides, so you can blame him. I think he basically hasn't decided which date it is, 3rd or the 10th. The February date is set. That is the 7th. The talk there will be mapping the heavens. And on March 7th will be another talk by Lauren Corliss from Johns Hopkins with a TBA title. You probably already noticed this, but there's still construction on San Martin Drive. So if you are coming from the south, it's pretty easy. But if you're coming from the north, you've either got to park on University Parkway or drive all the way around. So hopefully everyone found their way here. Easiest to approach from the south. But the good news is this will all stop in the new year. So hopefully this will be the last one of these where you have to worry about this. And this is the schedule. See, it says through December 2016. So hopefully so currently the red part and the yellow are the closed parts. The blue part is done. So anyway, the key is to approach from the south on San Martin Drive. Keep turning. I think weather does not permit us to go to the observatory, but that usually is something that happens afterward. I assume relevant people know what to do there. And I'm just going to give a quick introduction talk about a funny experience I had. Rather than, I know Frank sometimes does news and updates, I thought it might be fun to kind of tell you a tale of one of the most unusual observing runs I've been on. And it's called Why I Had a Boeing 747 Almost to Myself. So when people find out I'm an astronomer, the first question I invariably get asked in a kind of angry, aggressive tone is, why is Pluto not a planet anymore? People are really outraged by this, right? So, you know, the question you should be asking, and I'm sure that everyone here has thought about this, the real question is, what is a planet, right? Why is Pluto not one, or is it one? Why should we even be concerned about that? And there are many answers to this question about what is a planet. It could be, you could call it a round thing above a certain size. It could be something that orbits a star that doesn't, you know, have a larger object orbiting it or something. And there are lots of semantic definitions. But both Christine and I work in the field of formation of planets. And that's the way I think about planets, is a planet is something that formed around a star in its disk. So, I mean, these are the traditional planets, right? Planet was the definition of planet in 2006, was just something the ancient Greeks thought wandered in the sky. But the real thing to think about is when you approach a planetary system. I was having a fun discussion at lunch a few days ago about this. Let's say you were on the bridge of the Starship Enterprise or something like that, and you were flying into your star system and you wanted to say something useful about it, you were surveying it. What would you want to know? You'd want to know, what are the objects in orbit around the star? What are they made out of? What are they like? How many are there? And what temperature are they? What are their gases? Do they have surfaces? And what this is really a question about is, what we want to understand is, how do you form all of these different kinds of objects? Our solar system is a morass of different kinds of objects, ranging from planetary bodies down to dust particles. And the solar system as it looks today is this kind of neatly organized, mostly neatly organized system with the rocky inner planets, sort of an asteroid belt. That's not the only place where asteroids are, but that's one of the most common places to find them. The gas giant outer planets, objects from the Kuiper belt with askew orbits, ice dwarfs. And what's interesting is if you were to rewind the clock 4.5 billion years to when the solar system was less than 1 million years old, you probably would see it looking something like this. A swirling disk of gas with tiny dust particles hanging suspended in that gas, about 100 times as much gas as dust. And that is a planet-making factory. That's where solar systems come from. And we know this because we look at other ones. All of these are ingredients of things that have been found in space using space telescopes. Actually, going to skip this one. So how do we know that planets form in these disks? If you take a meteorite and you carve it open, as this actual meteorite shows, they are mashups of little pebbles that have been plasted together to build into bigger and bigger objects. This is the building blocks of planets. It may start big or it starts small, but whatever it is, you generate into these massive objects that we know today. So these are agglomerations. And Christine's going to talk, I suspect, quite a bit about this. So in order to study the infrared, the most powerful instrument ever developed for infrared study is the James Webb Space Telescope, which it will be controlled upstairs, just one floor above us, after it launches in 2018. About 2 minutes after that, control shift to this building. And we're all very excited, and it's a great tool for studying dusty, infrared, bright young stars. And here's a picture of me in front of the mirrors of the James Webb. So that's going to be in space, what's sitting right there. That's pretty amazing. Now, when I want to study young stars, there's one problem, which is that the telescope that I want to use is sitting in a clean room in Goddard Space Flight Center and not in space. So I had to use the current state-of-the-art in the infrared, which is airborne astronomy. So I'm going to talk not at all about the James Webb Space Telescope and tell you about another tale of a very unusual observatory. In Palmdale, California, with its many residents, and don't look too closely at the picture, you might see some that you recognize from other shows, is an area called Armstrong Flight Research Center, or Dryden Air Force Base. And in that Air Force Base is an airplane that NASA bought. It's not the Vomit Comet. So when people think of NASA airplanes, they ask me, oh, did you fly in the Vomit Comet? I said, that's exactly the opposite of what I wanted to do. Flying up and down like, we want super stable. This is why I would never do well in space. I would lose my contents of my stomach very quickly. So not the Vomit Comet. It's the Stratospheric Observatory for Infrared Astronomy, SOFIA. And what they did was they took a 747, and actually an old 747 from the 70s, bought it, and they cut a hole in the side of the plane. And in that hole is a telescope. So there's a telescope about 2.4 meters in diameter. James Webb is 6.5 meters for comparison. So this is small, but it's larger than most of our ground-based telescopes. And they carry it to 42,000 feet because the atmosphere of our Earth is one of the things that shields us from a lot of things, but it also makes infrared astronomy very tricky. So the less air that you have to go through, the better it is. That's why we usually put these things into space. Nice thing about an airplane is you can bring it down at the end of the day and do repairs and change out the instruments and things like that. And what's really neat is I can't go to James Webb or Hubble and use them directly. I can fly with SOFIA, and in fact, I did. It takes a lot of people to plan one of these flights. I have to tell you that on my flight, there were 2 flight planners, the 2 pilots, or pilot and co-pilot, there's sort of a midships person, 2 safety officers, 2 telescope operators, and 2 instrument scientists, and an outreach and education specialist. And then 6 teachers from the California Science Center who'd come along to check out how science worked. So it was about 20 people on the flight. And that's only a small fraction. When we went through the initial briefing, we had to come up with a flight plan. And so they came up with a plan. They have this map, right? So it takes off from Southern California. We can't fly over Mexico for various obscure legal reasons. So you have to avoid Mexico. You have to avoid military no-fly zones. And you have to fly in such a direction that you can observe your target. So think about this. Right, let me go back for a second. If you look at this airplane, so the telescope can only point out the left side of the plane. So you have to fly the plane such that the direction it's facing has the telescope pointed toward the star you want to look at, or the galaxy you want to look at. So you fly it in a straight line as long as you possibly can, pointing toward your target with no particular destination in mind. This drives air traffic controllers crazy. And one of the neat things is you have a headset, because I'll show you later, they ripped out all the insulation, so it's quite loud inside this plane. It's kind of like being in a noisy bar. But you get to listen to the pilot chatter with the very confused air traffic controllers. The call sign of the plane is NASA 747. You can follow it on FlightAware, every one of its flights, and they're all posted. And The so the trajectory you make you have to end up where you started. So you fly for 10 hours and end up nowhere. You've gone nowhere ultimately, but it's been quite a journey on the way. So each of the legs of this flight was a different target, and my two targets were when we were out over the Pacific. So we flew around into the Pacific, just skirting Mexico, kind of halfway out to Hawaii, up over Juneau, Alaska, and back down the entire west coast of the U.S. So we had contingency plans in case we had to land at Mexico City, Honolulu, Fairbanks. This was February, and I said, Fairbanks, are you insane? I have a light jacket on for Los Angeles weather. Like, if we had to land in Fairbanks in February, I think I would have, jumped out of the... Anyway. So we didn't. It all went great. This is me before we're getting ready to take off. I have a little protective reflector so that I don't get run over. You cannot point the camera this way. It turns out there's some other plane in the hangar that they don't want to show. No, I think it's some work they do for someone else. That was my seat for take-off and landing, those chairs at that table. And those are our headsets. So, when you fly in this thing, you kind of wait, and then they announce they're taking off, and they go, and you basically just go, pretty sharply upward to get to 42,000 or at least 39,000 feet as quickly as possible. And once you're up there, it is about 5 minutes in, they open the door for the telescope. They don't even tell you they're doing it. You would have no idea. It's perfectly pressurized. They open a hole in the side of the plane, and the telescope sticks out in its little harness, where it is kept, incredibly carefully in place. It's kind of an amazing technology. So we're not worried about wobble and stuff like that. It's basically under control. The safety briefing is a bit more extensive than you would have for a commercial flight, but it's a lot more comfortable. So you imagine 20 people in a plane, a 747, where they ripped out most of the seats and put in some computer desks, but it's a cavernous space, actually. So this is a pretty nice flight. It's a little cold because the insulation's kind of gone from a lot of the sides, and the back third of the plane is a telescope, but it's a pretty neat situation. This is actually, this picture made me nostalgic because the very first project I ever did as an undergraduate astronomer was to work with Dr. Terry Herter on the Forecast camera, which is the red instrument with the Cornell red bear on it. So when I was, about 20 years ago almost, when I was there, I was working on that. I can't say, I say working on it, I was doing a little bit of programming. Anyway, it was fun. It was really nice to be able to use the instrument that I remember being there for some of the testing of when it was first proposed. It's a long life cycle. So it sits, so the instrument is out here on the side that I'm on, but it's anchored to the telescope, which is on the far side of that sort of circular, safe-looking thing. So the telescope is inside on the other side in a shock frame. And from this side, you could just sort of see it adjusting and back and forth. Now, the key essentials on the flight are that they have a built-in coffee maker with like a bolt that holds the coffee. I don't know, I just imagined hot coffee whipping across the plane at hundreds of miles an hour or something, but nothing happened. There's a microwave oven, and so you bring your snacks on board and you can have dinner. And it's nice because they left some of the first class cabin seats, so observation's done, you can kind of take a nap. And you can go check out what we're looking at. So you can look at the stars, you can see what our targets are, our amazing science that was ongoing. And the best picture I got of the entire flight, I got to fly in the cockpit for a little bit at the top, the jump seat. And so that's a pretty open section plane. And the nice thing is when we were over Juneau, there were the northern, this is a terrible picture, but northern lights occupied the entire left side of the plane. So it was the most stunning view of the northern lights I'm ever going to get. So that was really probably the best picture of the flight. But we did get some data and some science happened, and this fun press release on gluttonous stars that you can read, and I'm happy to explain some other. And I happened, and I was really excited about the big news, and I hope to go back again soon. And in terms of the actual science that we discovered, I think I'm going to leave that to our main speaker. So let me introduce Dr. Christine Chen. So Christine did her undergraduate at Caltech. She's from California originally. She got her PhD from UCLA. Yes. And became a Spitzer Fellow. So she was working on the Spitzer Space Telescope. She was actually funded directly by their grants program. And she worked on that for a number of years where we collaborated on projects when I was a little wee graduate student. And then she became one of the MIRI instrument scientists here at the Space Telescope Science Institute in 2008. And she remained in that position until this year, where when she became the deputy project scientist for the entire James Webb Space Telescope. So she knows a lot about that, and she can tell you a lot about young stars and really cool stuff about planets. And take it away, Christine.
Thanks for the introduction, Joel. I'm going to talk about things that are very related to what Joel just kind of told you about. So in particular, like Joel, I'm an infrared astronomer, and I'm also interested in how planetary systems form and evolve. So Joel, the targets that Joel was looking at were fairly young stars that still have these nascent clouds of gas and dust and are still forming giant planets. The targets that I tend to look at are planetary systems that are somewhat older and that are perhaps more analogous to our own solar system, although systems can be young too. The defining difference between the systems that I look at and some of the ones that Joel showed you some nice observations from is the presence or absence of molecular gas. So if you think about the interstellar medium and what's contained in the region between stars, we know that it's largely gas and dust, with about 100 times more gas by mass than dust. And predominantly, a lot of this is contained in molecular hydrogen. For the systems that I'm going to talk about, we think that in the majority of them, the giant planets have already formed. And so in that process, all of the gas that we risk has accreted onto the star or accreted onto the atmospheres of Jovian planets or been expelled out of the planetary system. So these are much more analogous to our own solar system than protoplanetary disks. So if you were to try to take a high-resolution image of some of the systems that I study, these so-called debris disks, this is actually a picture that you might see. This is a picture that was obtained with the Hubble Space Telescope, the advanced camera for surveys. It has what's known as a coronagraphic instrument. Coronagraphs were developed to study the corona of the sun, and essentially what they contain is a physical mechanism, something mechanical, for blocking out the bright disk of the sun and allowing you to study the faint corona of the star or the sun. And in this particular case, what we're doing instead is we're blocking out the light from the central star in the planetary system. And by doing so, having the possibility then of detecting fainter material around the star, whether that is faint planets, Jovian mass planets, lower mass planets, you see is a ring of dust which is around the star. So this is the star Fomalhaut. It's one of the nearest stars to our sun. It's about 10 parsecs away, and this is an intermediate mass star. Its mass is about twice the mass of our sun. So when I think of these systems, this is kind of the typical kind of picture in my head, although many of the systems that we observe and try to learn about, we don't have such pretty pictures for. So this is just a quick outline of my talk. So again, many of these systems are very analogous to our solar system. So it's useful to stand back and to think about our solar system and the demographics of bodies in our solar system. So there are the giant planets, the terrestrial planets, there's asteroids and comets, and there's actually dust as well. So I'll tell you a little bit about the solar system dust, and then there's actually forces that act on the dust that rearrange the dust in our solar system. So for example, there's radiation pressure, which can blow dust outward, and there's also something called Poynting-Robertson drag, which is a relativistic effect, which causes larger dust grains to spiral into the central star. So I'll tell you about some of these forces that rearrange dust in our own solar system. So this population of dust that we see in our own solar system has now been, analogous populations have been seen around other stars, other main sequence, other midlife stars. And I'll tell you about some of the demographics from the early IRAS discoveries. And then Spitzer was a tremendous boon to this area of study, where IRAS discovered maybe about 100 targets. Spitzer told us about maybe 1,000, so an order of magnitude more, and gave us much more detailed spectroscopic information about these targets. And then because, as Joel mentioned, I worked on JWST, I'm tremendously excited about the gains that JWST will make, especially in this area of science, and I'll try to give you a hint of what that looks like. So I put this outline on top of this really beautiful picture of the night sky, and this is just to remind you of what the dust in our solar system looks like. So there is the zodiacal dust in our solar system, which is produced in the asteroid belt. And you can see it here at a time that's pretty much close to sunset, so that you're not looking very far away from the sun. But you can see from the dark side here, this is the Milky Way, and then you can see this sort of linear feature here in sort of reflected light. This is light that's reflected off of dust grains in our solar system. Again, this is called zodiacal light, and it's produced by sunlight scattered off of what's called the zodiacal dust. So this is just a reminder, Joel already spoke about this a little bit, about the bodies that we find in our own solar system. Of course, we're the most familiar with the terrestrial planets, and there are so many really beautiful images of the Jovian planets, and we've learned so much about them. But in addition to the planets, there's also a number of populations of minor bodies. So the ones that most people are familiar with are the asteroid belt. So these are kilometer up to tens of kilometer size bodies that live between Mars and Jupiter. And then in the outer reaches of the solar system, beyond the orbit of Neptune, there is the Kuiper belt. And the largest objects in the Kuiper belt have been named ice dwarf planets. So Joel also mentioned this controversy about what is the status of Pluto. So as you recall, it was originally a planet that has been reclassified as an ice dwarf planet. So for the most part, all of these objects lay in the zodiacal, in the zodiacal plane, in the plane of the solar system. But the last population, which is called the Oort cloud, actually lies in a spherical distribution around the sun. And these are small bodies that are sort of analogous to Kuiper belt objects, except for they've been scattered out to very large distances in all different directions from the sun. And this happens because the small bodies, for example, in the Kuiper belt, might have migrated into the inner solar system and then gravitationally encountered Jupiter or Saturn and then slung into the outer part of the solar system. So when I think about the solar system, this is what I think about. This is the part of the solar system that we're most familiar with, the inner 5AU with the terrestrial planets and the asteroid belt. And then moving out to the outer solar system, you can see the orbits here for the giant planets, the gas giants, and then this population of Kuiper belt objects. And both in the Kuiper belt and the asteroid belt, those small bodies collide, grind down, and produce dust grains. And then on larger scales, this spherical distribution of small bodies that makes up that Oort cloud. So I showed you a nice scattered light image of dust in our solar system. That beautiful panorama of the Milky Way, and then the zodiacal light. This is another way to look at the sky, and this is an image that was taken from the infrared astronomical satellite. So this was a satellite that launched in 1983, and it surveyed the entire sky in the infrared. So it mapped the sky at 12, 25, 60, and 100 microns. When you look at this map, it doesn't look like most maps that you're familiar with, because you're seeing the heat signature from bodies both in the Milky Way. So this is the galactic plane here, so this is our galaxy. And then also the heat signature for foreground closer objects. So this thing tilted here, this is dust, the zodiacal dust in our solar system. So you can see the plane of our solar system is canted compared to the plane of the Milky Way. So this is to illustrate that when you look at these maps of heat, you're seeing, in the far infrared, you're looking at maps of heat. And this is an incredibly efficient way to find dust, because the dust, for example, that's in our solar system, it absorbs sunlight from our sun, and that causes the dust grains to heat up to about 230 K. And then those dust grains re-radiate temperature, heat, which is detectable in the far infrared as light. What's particularly powerful is that with the dust grains is that if you think of a particular mass of stuff and small dust grains, you have a lot of surface area for those small dust grains compared to like a planet. So if, for example, if you were to imagine Jupiter broken up into micron-sized dust grains, there's much more surface area in those micron-sized dust grains compared to the planet Jupiter. And this is what makes it so easy to detect those dust grains then through the infrared thermal emission. So, if this is the zodiacal light, which was mapped so beautifully here by the IRAS satellite, interesting what is the connection between this dust and, for example, inner bottom. So this is a plot showing you the orbital parameters of asteroids in the main asteroid belt. In particular, the y-axis here shows you the inclination of their orbits plotted as a function of their semi-major axis. And every little dot on this plot represents a single asteroid. A plot like this was first made by an astronomer named Hirayama in 1918. And one of the stunning things that he discovered was that, and you can see this when you look at this more modern plot today, is that there is structure in this plot. So for example, there's a gap here, an absence of asteroids. This is the Kuiper gap. And so this is a location where if a body was here, it would be in resonance with Jupiter. And that resonance then makes the object unstable, gravitationally unstable, so it gets ejected out of that orbit. So that's why this whole region is clear. But in addition to structures like that, you can actually also see clumping of objects in this plot. And when this was first noticed, it was hypothesized that the reason why you have so many objects that are in these clumps is that they were originally part of a larger object that broke apart into smaller pieces. And so they still retained the overall same orbital parameters that you see on this plot. But there's now a little bit of dispersion from having broken up. You can imagine that when you have the breakup of an asteroid, you create not just large objects, but actually a whole size distribution of particles. So not just things that have sizes of 1 kilometer or 10 kilometers, but things all the way down to fine-grained dust, things with the size of a micron or so. And those are things that, again, have a lot of surface area for their mass, and so they're very efficiently warmed up, and they very efficiently re-radiate the heat, the energy that they absorb. And so one of the really interesting discoveries of the IRAS satellite was structures in the zodiacal light, in the zodiacal dust. And in particular, so these are sort of zoomed in pictures of the zodiacal light in which you can see that there's actually these bands where you have an enhancement of small particles in the dust in the inner part of the solar system. You can go through and model in better detail what the orbital parameters are associated with these dust bands, and you find that they're actually coincident with, for the particular case of these dust bands, the alpha, beta, and gamma dust bands, their orbital parameters are coincident with the Themis, Eos, and Coronis families. And so this tells you that these are the small particles that were formed when the larger body broke up. So not only do you see the large bodies in this asteroid plot, orbital parameter plot, but then you also see in maps of the sky the fine dust grains that are created when they break up. So, infrared, a lot of infrared astronomy is about detecting the heat signature from dust. And so I just wanted to remind you about black body emission and how it works. So this particular plot shows you intensity as a function of wavelength. So this side is blue and this side is red. For in this particular case, it would be stars of various temperatures. So 3,000, 4,000, 5,000, 6,000 Kelvin. So our sun has a temperature of about 5,800 Kelvin, so it's approximately like this 6,000 Kelvin star. So in the particular case of our sun, you can see that the peak of the light that comes out is at about 5,500 angstroms. It sort of corresponds to yellow-green. But if you imagine stars that have decreasing temperatures, the peak in this black body function actually shifts to the right. And so the energy that comes out for lower and lower temperature stars is redder and redder. So they have redder and redder colors. The other thing that you notice is that as you lower the temperature, the brightness or the intensity of the object also decreases. So when you lower the temperatures for things, the radiation becomes longer in wavelength, more red, and it also diminishes, lowers in intensity. So that's one of the major tools that we look at is detecting the heat, and I'll tell you more about the observations. For the dust in our particular solar system, it turns out that it doesn't really stay put from where it's generated. So you can imagine, for example, asteroids that collide together, and as they do so, they grind down and produce little tiny dust grains. It turns out that for the smallest grains in the size distribution, they have a lot of surface area for their volume. So they have a lot of surface area for their mass. And so that actually means that they're not gravitationally bound to the star. And so they act like tiny sails. And so the radiation pressure just drives them, blows them out of our solar system. And some there's a minimum size to the dust grains that are in our solar system. For dust grains that are larger, they're no longer sensitive to radiation pressure in this way. But what happens to them instead is they feel a relativistic effect called Poynting-Robertson drag. And in that particular case, you can imagine that you're a dust grain orbiting around the star. And as you do so, you feel a headwind of photons from the star. And that causes you to slow down, and so you lose angular momentum and you slowly spiral into the star. So the basic takeaway message is the expectation, or what happens in our solar system, is that the small grains get radiatively blown out and the larger ones spiral into the star. So it turns out that for our sun, there's another effect that brings large dust grains into the star. It's called solar wind drag, and this happens around active stars too. And in this particular case, it's very analogous to Poynting-Robertson drag, except for the difference is that the star is emitting not only photons, light, but it's also emitting particles, protons. So, and you can imagine now that what happens instead is that orbiting dust grain feels a headwind of these protons, of particles, which can cause them to slow down, lose angular momentum, and spiral into the star. So the main point is just that dust in the solar system gets rearranged in these different ways. So the part that really interests me is what do we know about planetary systems around other stars? Do we think that there are lots of other planetary systems that have analogous belts of small bodies? And you know, do they play some sort of role in how planetary systems form and evolve? So for example, if you think about our solar system and the Earth, one of the outstanding questions today is how was water delivered to the Earth? How did the oceans get here? And that's actually something that we don't understand well. And one of the ideas for the origin of the oceans was essentially they were delivered by comets from the outer solar system. So these minor bodies might actually be a very important source of water in extrasolar planetary systems. So the answer is that we've been able to discover minor bodies, so asteroid and Kuiper belt populations around stars. And we do this in the infrared. Particularly, this started with the IRAS satellite. So I showed you the beautiful all-sky image and then showed you the zodiacal dust bands. This was another one of the key contributions from the IRAS satellite. So basically, when IRAS was launched, the astronomers envisioned that they would use nearby A-type stars as calibrators, and they felt that they understood very well what the flux from those stars should look like based on how they look at visual wavelengths. And so basically, if you look at these plots, they're brightness flux as a function of wavelength, and you can see 12, 25, 1600 microns, so these are far infrared wavelengths. And these straight lines show you the expectations that people had for how bright those stars would be. And you can see these error bars show you the actual data. And what's really stunning is that these predictions for how bright the stars were or should be was a factor of 100 or so wrong for these 4 particular stars. And so when this was discovered, it was immediately hypothesized that the reason why they're so bright at 60 and 100 microns is because you have circumstellar dust, so dust around the star, which is absorbing, warming up, and radiating energy thermal emission. And so that's the understanding. And indeed, when astronomers were able to, once they identified these interesting candidate targets, so in this particular case, this is like Vega, Fomalhaut, Beta Pictoris, and Epsilon Eridani, they would go to other facilities and then try to take a picture of the planetary system. And so one of the first ones that they were able to do this successfully for was Beta Pictoris. This is a more modern image taken with the Hubble Space Telescope with the STIS coronagraph, in which the star has been placed behind an occulting wedge, and you can see that there's this bright linear feature. This is a disk that's being seen edge on. And then you can see a different stretch here, which shows you more clearly this edge-on disk. So this, again, is what you're seeing is heat from small dust grains in this particular system. The really interesting thing about whenever people go out and take images of the system at higher and higher angular resolution is they find detailed structures that imply the presence of planets. So in this particular case, in the case of Beta Pictoris, what you can see is that the inner part of the disk is warped with respect to the outer part of the disk. One of the hypotheses for why this is true is essentially that there is a companion, that is a planetary mass-sized thing in this planetary system, which disrupts the dust and forces the dust onto these inclined orbits. If you look at the distance of this warp compared to the star, you can then place constraints on the product of the mass of the planet and its distance from the central star. And one of the really exciting things is in the 20 or 30 years of studying these particular objects, people have been able to refine their understandings of these planetary systems. And so this is now a even more recent image of the exact same system. This is now ground-based data taken with a very large telescope, ESO, the European facility in Chile. And it's a composite image showing you the disk. But now you also see, so the disk is taken with a coronagraph, but now you also see images of a point source that were discovered very close to the star at about 10 AU from the star. This position on the sort of left side here was the discovery epoch, and then it appeared to disappear for a while. And then it reappeared, so it first was detected in 2003 and then reappeared in 2009. And so you're actually seeing then the orbital motion of a giant planet in this particular disk, which is consistent with the structures that were seen in the dust from the older Hubble Space Telescope images. So why do we want to go out and try to study these particular planetary systems? We already learned so much from Kepler and looking at the demographics of planets that are detected through transit or radial velocity or other things. And the answer is that it gives us complementary information. It's very hard with planets to understand what the detailed composition of the planet is because really all you ever measure for like the transiting planets is the mass and the radius, and so you get the density of the planet. But in the case of these particular systems, you have the opportunity to actually measure the detailed composition of the material and understand what's really made of. And it also provides insight into particular epochs that were very violent in the formation of our own solar system. And so early on in terrestrial planet formation within the first 30 million years, there were a lot of violent collisions in which things collided together to build up larger and larger things to form Earth. And then at ages of 30 to 100 million years, we know that there were giant collisions in our solar system. So for example, we knew that a Mars-sized object called Theia impacted the Earth and formed the Moon. And so, by studying these other systems, we can understand whether these events in the history of our solar system are common or rare. So this is just meant to be a nice simulation I mentioned to you how giant impacts were important in the history of our solar system. I'm having a little bit of trouble. There it goes. And so this is just a simulation of the moon forming impact. and in which the Theia-sized body ran into the Earth on a glancing sort of collision course. And what you see here is basically the mantles of the two objects mixed together, spin off and condense and eventually form into the moon. And then the core of the impactor actually sunk into the forming Earth. And so this explains a lot of what we know about the properties of the moon. So, for example, the Apollo astronauts went and collected lunar samples and analyzed composition of those, and it turns out they're very similar to the mantle of our own Earth. So we can try and learn about these violent things that happened in our solar system, whether they're giant collisions early on, or we also think that there was an interesting period in the evolution of our solar system called the period of late heavy bombardment, and that this happened when our solar system had an age of about 700 million years. This is preserved in the crater record of old terrestrial surfaces, such as the moon, and so these are maps showing you highlighted craters left over from the period of late heavy bombardment at about 700 million years. So the prevailing idea for how these craters got to be there is essentially that the giant planets, the locations that we see them at today, are not the locations at which those giant planets formed. The giant planets actually migrated from a different location to where they are today. And as they did so, Jupiter and Saturn crossed the 2-to-1 resonance. And basically, the resonance crossing destabilized all of the minor bodies in our solar system, such as the asteroids in the Kuiper belt. And so basically, all of the minor bodies became chaotic for a brief period, and they went all throughout the solar system. And this is sort of, you can sort of visualize that in this simulation here, where the rings show you the orbits of the 4 outermost planets. And initially you saw all those green dots, which were, each one represents a Kuiper belt. And then you can see the moment when you cross the 2-to-1 resonance, and all of those things get destabilized, and they go everywhere in the solar system. So these are the kinds of periods in the history that we're trying to study. So the tool that I used, and Joel used as well, was the Spitzer Space Telescope. Spitzer launched in 2003. It was cryogenic, or 2004, it was cryogenic. It was literally cooled to about 4 Kelvin, but it was a relatively small telescope. It was only 85 centimeters in diameter. But because it was so cold and in space, it had tremendous sensitivity compared to any other facility working at those wavelengths prior. So wavelengths of a couple microns to 160 microns. And it really enabled for the first time solid state infrared spectroscopy of large samples of young disks. And so that's an excerpt from a paper basically trying to illustrate what these solid state features from silicates like olivine look like in the infrared. So basically you get a peak. This is like an emission feature around 10 microns and another one at 20 microns. It's really fascinating because just like atoms, when you can tell the composition of a gas by looking at the spectrum from it, you can tell the composition of the dust material by looking at the peak position of, for example, of the material that you see the spectrum for in the infrared. But more than that, not only can you tell what it's made of, but you can actually also tell how large the dust grains are. So it turns out that the feature actually changes shape. So again, this is brightness as a function of wavelength, but the feature changes shape depending on how large the grains are. So for small grains, the feature is sort of triangular, so it's tall and pointy. And as the grains grow, the feature actually becomes more broad and trapezoidal in shape. And so by fitting the shapes of these features, you can tell the composition of the dust, and you can also say how big the dust grains are. So these are some examples of spectra from targets that I was interested in, which actually help to constrain the evolutionary phase of these particular objects. So again, this is flux as a function of wavelength, and then this is again that 10 micron feature, and then here it's harder to see the 20 micron feature, but again the 10 micron feature and the 20 micron feature. You can see in this particular case, it's not purely just simple olivine processing simple silicates. There's a number of different materials that go into modeling this particular feature, including materials that are altered at high pressures and temperatures. So things like obsidian that you find on Earth, or tektite that you find in the eject envelopes of craters, and possibly SiO, silicon monoxide gas. This is the sort of feature that might be indicative of a giant hypervelocity collision. So a collision in which you have a moon-forming event because you produce all of this material that's altered at high pressures and temperatures in the terrestrial planet zone. This is in contrast to something that has a feature like this, where you can see the 10 micron feature, the shape of it looks really, really different. And this is because when you decompose it, it's made out of instead things more like water and amorphous carbon. And so these are very pristine things that you might expect to find in the outer solar system. So this might then tell you about a Kuiper belt object from the outer solar system coming into terrestrial planet and disintegrating or colliding with a terrestrial planet, producing this sort of spectral feature. Spectroscopy, although it's not as pretty to look at as nice pictures, can actually tell you a lot of really detailed diagnostic information about the composition and the evolutionary phase of the target. But you can learn not only about the composition of the targets, but also about the spatial distribution of the dust. And this is really relying on the fact that when you look at dust in these systems, the dust that's closest to the star is actually warmest, and the dust that's further away is actually coolest. So this just kind of gives you a broad idea. So if looking at 0.1 AU, this radiates most strongly at 1 micron, whereas this material here that's at maybe about 100 AU from a solar-like star radiates more strongly at 1,000 microns. So basically, in the absence of having a picture that shows you where all the dust is located, you can take measurements of the brightness as a function of wavelength and try to invert them to figure out where the dust is located. So that was a project that I carried out with an undergraduate student here at Johns Hopkins. We looked at the spectra of some 500 stars. And each one of these postage stamps is the brightness as a function of wavelength for a bunch of stars. And you can see there's these strong sources on the blue side. This is the emission from the star. And then the gray things are the emission from the dust. And so you can see that in a lot of cases, there are sources for which there's not dust, but there is dust pretty far away. And this tells us basically that there is an inner region that's devoid of dust. And one of the possibilities for why there's no dust there is that there's a giant planet, which is basically clearing the inner part of the planetary system from dust. So just to look at a more detailed example, this is, again, one of these spectral energy distributions, brightness as a function of wavelength for a particular star, which is HR 8799. And you see here's the big bump from the emission from the star. And then the red stuff here, these are data points, and it's hard to see, but there's some blue data points too. But you can see that at the long wavelengths here at 30 microns or so, that you get emission that's in excess of what you expect from the star, and then it actually turns upward a little bit, and then there's these bright points here. Essentially, when you try to do the analysis of the heat from this system, you require having two components, a warmish component and a coldish component. And this is very analogous to like what you might expect our solar system to look like to an observer far away. We have the asteroid belt and the Kuiper belt, and then a family of Jovian planets that live in between. And in this particular system, you're seeing kind of the same thing, an asteroid belt and a Kuiper belt and some space in between. And so that seems like a really good place to go look for planets. And indeed, there are some astronomers using the Keck telescope in Hawaii, and they weren't using a chronograph, but essentially they were having to subtract out the emission from the star so you could see faint things. So that's why there should be a bright star in here, but it's been subtracted out. But they actually discovered the presence of 4 Jovian mass planets, so planets with masses about 10 Jupiter masses, in orbit around this particular star. And those planets happen to fall right in between where the asteroid and Kuiper belts are for this planetary system. So we know that there are planetary systems with architectures like our own, but we don't really understand maybe what the context is for our solar system. How common is it, or how rare is it? So one of the reasons why I'm tremendously excited about the James Webb Space Telescope is you can just tell by looking at this particular graphic, right? This shows you to scale the difference between the Spitzer Space Telescope and the James Webb Space Telescope. So Spitzer was an 85 centimeter telescope. JWST is going to be a 6.5 meter telescope. Spitzer was phenomenal for this area of study in being able to survey a large number of stars, to be able to discover more than 1,000 planetary systems with asteroidal or Kuiper belt dust in them. But what JWST is really going to bring to the table is, because it has such a much bigger mirror, it has much better angular resolution. And so now, instead of seeing an unresolved point, you'll actually be able to look at where the dust is as a function of position, map out the dust in these planetary systems. And it'll do this for hundreds of nearby stars. This is just a direct comparison of what our expectations are. So this top panel here, this is actually data from the Spitzer Space Telescope. This was obtained by Kate Sue and her collaborators. This is data for the Vega system, which was observed at 24 microns. And you can see here, because the resolution for Spitzer is so poor, essentially you take that poor resolution and convolve it with this planetary system, and you just get a big blob. But JWST, we expect to have much better angular resolution. And so this panel here shows you simulations of what the possibilities might actually be for the configuration of the dust in this system. This is taking advantage of coronagraphs on board JWST to block out the central light from the star. And so on the left-hand side, you see a top model and a bottom model. And this is without what's called point spread function PSF subtraction. So this is if you were just to use the coronagraph and put the star behind the center of the coronagraph. And then what people do to improve their images is essentially they observe their target star with the coronagraph, and they observe another star with their coronagraph, one that doesn't have anything around it, and they subtract those two images so that they can remove the residual stellar light and then dig in deeper close to the star looking for additional material. So these are PSF subtracted images, simulations instead. And then you can see there's two flavors of models here, one where the dust is symmetric, and here it's not. The key things that you notice here you don't see this inner hole in the disk. That's expected to be seen based on what the spectral energy distribution looks like. And then also we have questions about what is the detailed distribution of the dust. Is it symmetric or is it asymmetric? There's a possibility that there's a planet in this particular system, and it traps asteroids or Kuiper belt objects into exterior mean motion resonances, and that those bodies collide and grind and produce dust grains, which are radiatively driven out by radiation pressure and blown into these spiral structures that then you might be able to actually see with the James Webb Space Telescope. So we're tremendously excited about what we can do. The other thing that's really exciting is before I showed you some spectra obtained with Spitzer, and it was just a spectrum of the whole planetary system. But because James Webb Space Telescope has this phenomenal angular resolution, you'll actually be able to take spectra of all the different points in the field, because you'll spatially resolve the whole planetary system. And so you'll be able to look for gradients in the composition of the dust grains as a function of position. So this has actually been carried out for one planetary system, Beta Pictoris, the first one that I showed you, that had that edge-on disk. This has been done from the Subaru telescope in Hawaii. And essentially, these are spectra from different little positions in the disk, right around 10 microns where that silicate feature is. And if you squint really hard, you can see that the shape of this 10 micron feature actually changes as a function of position along the disk. And it tells you where the small grains are located in this disk. It turns out that they tend to be, it looks like that they're predominantly in 3 large rings. And it also tells you where the crystalline material is, so where the dust grains that have been annealed by interactions with the star are located, and they tend to be located near the orbit center. So I just think the spectroscopic power of JWST is absolutely amazing. So not only will we be able to take these kind of spatially resolved thermal emission spectra, but we'll also be able to take, hopefully, spatially resolved scattered light spectra. So now instead of looking at the spectrum from the heat generated by these dust grains, you'll be able to look at the spectrum of the reflected light from these dust grains. And this just shows you, there's an instrument on board called the near-infrared spectrograph, NIRSPEC, and essentially it has an image slicer, so it divides the field of view up into all these little tiny rectangles, and then basically it disperses the light from each rectangle. So in this way, you'll be able to take spectra at different positions for in particular this particular disk. And this is really interesting in the near-infrared, because in the near-infrared you have access to solid-state features now not from silicates, but from ices. And I think ices are tremendously exciting because, as I mentioned before, we don't understand what the origin of water is in our solar system. And it would be very interesting to understand what the reservoirs of water around other planetary systems look like and whether or not they have the potential to deliver oceans to terrestrial planets there. So this is just my last slide. Just the key points that I wanted to say were these debris disk systems that I've been showing you the data from. They're analogs of our solar system when it was young or middle-aged, and around young stars. Mid-infrared spectra that we saw, these disks, reveal these solid-state features that indicate that the dust is composed of silicates. So these are things like olivines, like real materials that we're familiar with on our own planet. So for example, if you go to South Point in Hawaii, you can see the olivine, the green sand beach there, and it's the same materials. Spectral distribution analysis, so that was that flux of functional wavelength analysis, indicates the majority of these debris disk systems possess structure. That means that they have these central clearings, these regions close to the star that are devoid of dust. And it tells us that there's probably something in those cleared out regions that's clearing them out, such as a Jovian planet. So planets may be forming or may have already formed in these systems. So thank you for your attention, and I'm happy to take any questions people might have.
Questions for Dr. Chen?
Yeah, I have a question about the asteroid belt in our solar system and elsewhere. Are two opposite things going on at the same time in there, with dust accreting into larger objects and larger objects being broken apart?
Yeah, so it basically, the key thing that's important is the dispersion velocity, so the relative velocity between the particles. So if the relative velocity is relatively low, then things tend to stick. But if the relative velocity is very high, then things tend to shatter. So if you think about the early phases of our solar system, the phase that Joel told you about, when there's a lot of gas in the disk, everything is sort of entrained in the gas, and so it moves at approximately the same velocity, and the relative velocities are very low. And so during that phase, especially when you have a lot of gas in the disk, you're in a really strong building phase. But once the gas is dissipated, you no longer maintain similar velocities of the material going around the star, and so you can get fairly high relative velocities. So things can be going in different directions at fairly good speeds, so that when they actually hit, it's destructive rather than constructive.
But the speed that they're traveling is determined by the distance from...
Right, but there's a little bit of a, I mean, it's not just, so you're thinking about Kepler's law. But I mean, in addition to, it's not just the orbital velocity, because everything doesn't orbit in a perfect plane, right? And so there's different semi-major axes, inclinations, eccentricities.
I mean, you're in a pile of goo, right? You're at this gas, and you're traveling through molasses. That is going to let things sort of gently roll into each other. Whereas if you take the gas away, it's open season. It's like firing a bullet underwater versus air. Yes.
Has the existence or the apparent existence of a new planet 9 shown up in any of your research?
Oh, that's really interesting. So I think you're...
Repeat the question.
Oh, sorry.
Oh, okay, I'll repeat the question. Sorry. Am I? All right. The question was, does any of your research focus on potentially large planets in our own solar system that we haven't found yet, like Planet 9, that could be way out in these debris disk regions?
Yeah, so Planet 9 is really fascinating. And unfortunately, so I tend to focus on extrasolar planetary systems, so planetary systems outside of our own. But what you're referring to, of course, is there's been this really fascinating work, partly out of Caltech by Mike Brown, and I'm blanking on the other fellow's name.
Mike Brown, the Pluto killer, I believe?
The Pluto killer, yes, exactly. Where essentially he was, so you may know him as the discoverer of a lot of these ice dwarf planets in the outer solar system. And when he was looking at the orbital properties of those ice dwarf planets, he noticed that there was sort of this coincidence in their orbital parameters. That is, they were all sort of grouped together in one place. And you would sort of expect, you might naively expect that they should have sort of more random orbital parameters. And so one of the hypotheses essentially that he's been advocating is that there is additional planet that is heretofore undetected, which is essentially interacting gravitationally with these ice giants and forcing them into these sort of aligned orbits. Yeah. There's actually a fabulous, I should advertise this, Mike has this fabulous Coursera course. I don't know if you've ever seen Coursera, it's an online learning thing. But he has a class called Physics of the Solar System or something like that. And he actually spends 2 weeks talking about small bodies in the outer solar system of our solar system. It's a great class. He's a really engaging lecturer. I think he spends the first 4 weeks talking about Mars. And then I think he talks about life in the universe too.
And that hypothesized planet would be quite large, right? I think it's not Pluto.
No, it's like a terrestrial planet. It's like an Earth-sized. I think it's an Earth-sized thing.
Yes.
I'm curious about this slide where you had the spectrograph, the IR spectrographs.
Yeah.
The accretion disk, I guess.
Well, these are debris disks. They're debris disks, so they're older. So they're this phase. So an accretion disk means that you have stuff accreting onto the star. So that inherently means that there's gas in the disk, and so all that material is entrained and going onto the star.
This is more like analogous.
It's more like a solar system. Yeah.
I was curious whether the single lines on the bottom are what you're using to create the best fit model, or your best fit model of the data that you found to determine what is, like,
How does the modeling work? Yeah. So basically, this is work that was carried out by my friend Casey Lees at APL, and he has this huge library of emissivities of different materials. And basically he does like a minimum chi-squared analysis. So he takes all of these components and tries to add them up in some sensible way in order to reproduce the features best as he can. So you can see in some cases that this might be successful if like there are features that are at distinct wavelengths so that they can't be created by anything else. But you can see that there are a lot of things where you might have spectral features that are overlapping. And so one of the frustrations with this kind of analysis is actually it's somewhat degenerate. And so you can imagine different mixtures of materials giving rise to the same feature. Yeah. And so when people do this kind of analysis, basically they have to, if they're being very rigorous about it, they'll go through and do a Monte Carlo analysis. And then basically they'll show you like a probability distribution function. So the likelihood that you have any given material. So it's not just like, oh, it's like 50% is this. It's like, the most likely model is that 50% of it is that, but there's also some probability that it's like 30% instead. So yeah.
Just to clarify for the audience, so the non-experts, the lines at the bottom, these olivines, obsidians, etc. Yeah, when you say they're a library, that means that they were measured by
in the laboratory.
So on Earth, someone took one of these rocks, used a spectrograph to create an actual lab spectrum of that rock, and then we're using it as a fingerprint for space-based ones. Yes.
Could you unpack how comets, further explain how comets could be the source of the ocean?
Yeah,
the question was about comets and the source of the oceans.
Yeah, so that's actually a really fascinating field of research. So basically, one of the things about the Earth that we don't really understand well is like how much water is on Earth, because water is incorporated in the Earth at many different locations, including in the deep interior. And so the exact amount of water is not known. One of the ways that people have tried to diagnose the fundamental problem is if you look at the location of the Earth where it is today and assume that it formed there, essentially the proto-Earth is too hot to basically retain water vapor. And so the going in hypothesis for people for decades has been that the Earth is formed dry because of this. And so that means that like the water had to come from somewhere else. And so for a long time, people had considered comets as the source of water in the ocean. And one of the diagnostic ways that they would try to figure out whether or not this was true was looking at the deuterium to hydrogen ratio in mean ocean seawater. And compare that to the deuterium to hydrogen ratio in comets to see if at all they were common. It turned out for a long time the distribution of comets that people were probing, which I think were from fairly far out in the solar system, they actually had a higher deuterium fraction, I think, compared to mean ocean seawater. People were uncertain, that was not the most accurate explanation for water on Earth. It is still a really active field of research. So there was more recent data taken by the Herschel Space Telescope around 2010 or so of some of these Trojan objects instead. And those actually tended to have D/H ratios that were more similar to mean ocean seawater. So people are not sure what the origin of water on the Earth is. So that's one possibility. Another possibility that's, I think, become more in vogue is the idea that the water was actually delivered by water-rich asteroids. So that scenario that I told you about the period of late bombardment and how the migration of the planets destabilized the minor bodies in our solar system. It destabilized all of them, including, we think, the asteroids in the main asteroid belt. The asteroids that are a little bit further out, the asteroid belt, are expected to be somewhat rich. And so they have been hypothesized as another source of water for the oceans on Earth. We think we have evidence for collisions between those objects and the inner solar system when you look on like the moon or Mars. So how many big craters versus how many little craters on the moon or Mars or something like that, and look at the size distribution of asteroids, how many big asteroids versus little asteroids. And it turns out the size distribution of asteroids in the main asteroid belt lines up with the size distribution of craters on old terrestrial surfaces. So we know those things got slung in during the period of late heaven bombardment. And based on some of the spectroscopic analysis, we think they're water rich too. So they're another, I think right now they're actually probably the more favored source of water on Earth.
What about burning of hydrocarbons? That produces water also.
Right, but that's a small, yeah.
Yes, back there.
Could you go into a little more detail on these ice planets and alleged planet number 9?
More question about more clarification for icy planets and Planet 9.
Yeah, that's correct. And so when this whole controversy was going on about Pluto, essentially what happened was, Pluto was discovered, I think like in 1930 or so at Lowell Observatory. And, for a long time, it was the only thing kind of known in the solar system. And basically in the 1990s, Dave Jewett and Jane Liu went out and basically carried out these deep surveys of the sky, of the ecliptic plane, looking for additional minor bodies out there. And so this led to the discovery of the whole population of Kuiper belt objects. And so when the Kuiper belt objects were discovered, and this is again some of Mike Brown's really beautiful work, they discovered that some of the largest Kuiper belt objects were even bigger than Pluto, right? And so then there became this sort of thing, well, do you consider them planets too? And the thing that made them very similar to Pluto was, so Pluto is in a 3:2 resonance with Neptune. And it turns out there's a whole family of other Kuiper belt objects that are also in the 3:2 resonance. So Pluto doesn't have a particularly unique mass or size compared to things in the Kuiper belt region, and it doesn't have a particularly unique orbit. And so that was part of the reasoning that the IAU used to demote its status from a planet to a Kuiper belt object, because they said, hey, there's so many more of these other objects that are out there. It's really not that special, and maybe it's really one of these other Kuiper belt objects, and there's a whole like half a dozen of them that instead we're going to designate as ice dwarfs. So things like Sedna and other stuff.
Or Haumea.
Yeah.
What's the connection though with this alleged planet?
Oh, okay. So this is not my field of expertise, but essentially what I recall of Mike Brown's analysis is essentially he was looking at the orbital parameters for all of those large objects, maybe like the largest 9 or 12 of them or something like that. And basically, he noticed that, again, if you expect them to be randomly scattered out or something, they should be all over the place. But he noticed when he made this orbital parameter plot that they were all sort of clumped in one area, or at least avoid a particular area of the phase space. And so based on the dynamical evidence, like what the orbits look like, essentially, that's where the hypothesis for this Planet 9 came from, that basically it's exerting a gravitational influence on these large objects. We don't see it directly, we just see how the other objects feel its presence. So I really recommend to you, I think part of that Coursera class that Mike Brown has, I think it starts up every 3 months or something like that, because he and his colleagues are the I think he has a lecture in this course about, it's actually a really excellent class. So if you're interested in the solar system generically, there's a beautiful, the first 4 weeks are about Mars. I hadn't seen the detailed radar maps for Mars, and seeing how much geology people now know from Mars. It's really spectacular. I highly recommend it. Yeah.
Other questions? Yes.
Okay, so you're having dust spreading out and then dust accreting.
Mm-hmm.
So if you have a planet like Jupiter, is that shrinking or gaining mass?
So in the particular case of Jupiter, Jupiter is so massive that essentially it tends to use gravity affects things that try to come into where it's located. And most of the time, if an object comes in the outer solar system toward Jupiter, it encounters Jupiter, and it's a little bit counterintuitive, but it's actually gravitationally slung out of the system. So most of the time, Jupiter doesn't, it doesn't either gain or lose mass. But for smaller objects, for some objects, so Comet Linear several years ago, or even, was it the one Shoemaker Levy that impacted Jupiter in the late 90s? Yeah. That was a clear case of material being accreted onto the planet. Yeah.
That was
so it
one
depends.
that Hubble had a ringside T2. That's why.
Right. So,
Nobody's really been able to measure it.
So, well, I mean, I think that's an active area of research where people actually do real dynamical simulations, right? Because they're curious what happens when you implant a planet in a planetary system and watch dust come in, and how does it affect it? Because if it's a small planet, you can imagine the gravity's not so great, and so it doesn't affect it as strongly as like a big planet like Jupiter.
Any other questions? Yes.
Sure.
Question about the late heavy bombardment. What was it?
So this is that's been talked about for a while. Essentially, people noticed a long time ago that when you looked at old terrestrial planet surfaces, so the surfaces of Mercury, Mars, and the Moon, that they had a lot of craters on them. So this is just a map of the near side and the far side of the Moon, and you can see the craters are picked out so you can see them more easily. On the Moon, you can see there are periods where there's been geologic resurfacing, where lava has come up to the surface and formed maria, the seas that you see on the surface of the Moon, right? And so it was, based on observations like that, you knew that there was a violent period in the early part of the solar system where you had a lot of collisions, and you could kind of constrain when that happened based on looking at where the properties of the maria, right? One of the things that people have been struggling to understand for a long time is when those observations were first made and noticed, people sort of thought that all of these collisions happened at the same time. Like it was kind of like a delta function. When all the cratering, like all the collisions went up, you know, the collision rate went up really high. It just went up really high and came down really fast. There's been a lot of really nice work by a researcher named Bill Botke, particularly you know, studying these surfaces and trying to understand this cratering period. And honestly, I don't remember the exact details, but my impression has been that over time, our thinking of the cratering record is that, you know, essentially these craters are actually formed over time. Essentially, you know, people then are, of course, very interested in what are the mechanisms to create the craters. And so this idea that I was describing for you, this is actually called the Nice model because it was first hypothesized by a number of astronomers in Nice, France. And essentially, it basically tried to account for a number of things, observations that people made of the solar system that seemed sort of startling. So one of them was, for example, when you look at the mass of the asteroid belt and compare it to the mass of the terrestrial planets and the Jovian planets around it, if you were to smooth out all of that mass, you actually get a divot in the amount of stuff around the asteroid belt. And so people knew essentially that the asteroid belt, the primordial asteroid belt, was actually a lot more massive than the asteroid belt that we see today. Then this sort of leads to the question of like, well, what happened to all of those objects, right? And so, you know, it was noticed that there were these Kirkwood gaps that I talked about, where you have mean motion resonances, where you lose material. But this Nice model, which has really come into fashion in the past years, describes a lot of reasons why you see certain properties of the solar system, such as diminished asteroid belt, has become the leading explanation. So again, this is that the location of Jupiter and Saturn in our solar system today are not the locations where Jupiter and Saturn formed, and that Jupiter and Saturn migrated from their formation locations to their present-day locations. And as they did so, they crossed the 2-to-1 resonance. So this means that for every 2 times Jupiter goes around the sun, Saturn goes around once. And when you do that, it actually destabilizes the orbits of the minor bodies because they get, this gravitational pull that's exacerbated by the 2 planets because they're both in the same position. It's like they both come around to being at the same place around the sun, right? So that's what destabilizes the minor bodies. So basically, I spoke a little bit of some of the sort of planetary science evidence for this. So for example, one, we think the asteroid belt had to be more massive. 2, when you look at the size distribution of craters on like the moon, it matches with the size distribution of bodies in the main asteroid belt. So that tells you that the projectiles are consistent with coming from the main asteroid belt. So it's really become like the accepted sort of mechanism describing the period of late heavy bombardment today.
I think we have time for one final question, if there is one. I think maybe we've done it. All right. Well, thank you everyone for coming. Thanks again to Dr. Christine Chen, and see you in a month. If it's the 10th, yes. If it's the 3rd, no. If it's the 3rd, I'll be in Texas. In fact, we'll all be in Texas. So, I mean, these are the traditional planets, right? Planet was the definition of planet in 2006, was just something the ancient Greeks thought wandered in the sky. But the real thing to think about is when you approach a planetary system. I was having a fun discussion at lunch a few days ago about this. if you, let's say you were on the bridge of the Starship Enterprise or something like that, and you were flying into your star system and you wanted to say something useful about it, you were surveying it, what would you want to know? You'd want to know, what are the objects in orbit around the star? What are they made out of? What are they like? How many are there? And what temperature are they? What are their gases? Do they have surfaces? And what this is really a question about is, what we want to understand is, how do you form all of these different kinds of objects? Our solar system is a morass of different kinds of objects, ranging from planetary bodies down to dust particles. And the solar system as it looks today is this kind of neatly organized, mostly neatly organized system with the rocky inner planets, sort of an asteroid belt. That's not the only place where asteroids are, but that's one of the most common places to find them. The gas giant outer planets, objects from the Kuiper belt with askew orbits, ice dwarfs. And what's interesting is, if you were to rewind the clock 4.5 billion years to when the solar system was less than 1 million years old, you probably would see it looking something like this: a swirling disk of gas with tiny dust particles hanging suspended in the approach from the south on San Martin Drive. Keep turning. I think weather does not permit us to go to the observatory, but that usually is something that happens afterward. I assume relevant people know what to do there. And I'm just going to give a quick introduction talk about a funny experience I had. Rather than, I know Frank sometimes does news and updates, I thought it might be fun to kind of tell you a tale of one of the most unusual observing runs I've been on. And it's called Why I Had a Boeing 747 Almost to Myself. So when people find out I'm an astronomer, the first question I invariably get asked in a kind of angry, aggressive tone is, why is Pluto not a planet anymore? People are really outraged by this, right? So, you know, the question you should be asking, and I'm sure that everyone here has thought about this, the real question is, what is a planet, right? Why is Pluto not one, or is it one? Why should we even be concerned about that? And there are many answers to this question about what is a planet. It could be, you could call it a round thing above a certain size. It could be something that orbits a star that doesn't, you know, have a larger object orbiting it or something. And there are lots of semantic definitions. But both Christine and I work in the field of formation of planets. And that's the way I think about planets, is a planet is something that formed around a star in its disk. Holiday greeting cards, one per person, and there might be a few extras left at the end. Our speaker tonight, who will be speaking, I'll give a short introduction prior to that, and our speaker tonight will be Dr. Christine Chen. I'll introduce you in a moment as we get through. And she will be talking about debris disks and the formation of young planetary systems. Upcoming public lecture series talks are January 3rd or 10th. I guess it's TBA. I think that's why Frank gave me these slides, so you can blame him. I think he basically hasn't decided which date it is, 3rd or the 10th. The February date is set. That is the 7th. The talk there will be Mapping the Heavens. And on March 7th will be another talk by Lauren Corliss from Johns Hopkins with a TBA title. You probably already noticed this, but there's still construction on San Martin Drive. So if you are coming from the south, it's pretty easy. But if you're coming from the north, you've either got to park on University Parkway or drive all the way around. So hopefully everyone found their way here. Easiest to approach from the south. But the good news is this will all stop in the new year. So hopefully this will be the last one of these where you have to worry about this. And this is the schedule. See, it says through December 2016. So hopefully so currently the red part and the yellow are the closed parts. The blue part is done. So anyway, the key is which is airborne astronomy. So I'm going to talk not at all about the James Webb Space Telescope and tell you about another tale of a very unusual observatory. In Palmdale, California, with its many residents, and you don't look too closely at the picture, you might see some that you recognize from other shows, is an area called Armstrong Flight Research Center, or Dryden Air Force Base. And in that Air Force Base is an airplane that NASA bought. It's not the Vomit Comet. So when people think of NASA airplanes, they ask me, "Oh, did you fly in the Vomit Comet?" That's exactly the opposite of what I wanted to do. Flying up and down like we want super stable. This is why I would never do well in space. I would lose my contents of my stomach very quickly. So, not the Vomit Comet. It's the Stratospheric Observatory for Infrared Astronomy, SOFIA. And what they did was they took a 747, and actually an old 747 from the 70s, bought it, and they cut a hole in the side of the plane. And in that hole is a telescope. So there's a telescope about 2.4 meters in diameter. James Webb is 6.5 meters for comparison. So this is small, but it's larger than most of our ground-based telescopes. And they carry it to 42,000 feet because the atmosphere of our Earth is one of the things that shields us from a lot of things, but it also makes infrared astronomy very tricky. So the less air that you have to go through, the better it is. That's why we usually put these things into space. Nice that gas, about 100 times as much gas as dust. And that is a planet-making factory. That's where solar systems come from. And we know this because we look at other ones. All of these are ingredients of things that have been found in space using space telescopes. Actually going to skip this one. So how do we know that planets form in these disks? If you take a meteorite and you carve it open, as this actual meteorite shows, they are mashups of little pebbles that have been plashed together to build into bigger and bigger objects. This is the building blocks of planets. It may start big or it starts small, but whatever it is, you generate into these massive objects that we know today. So these are agglomerations. And Christine's going to talk, I suspect, quite a bit about this. So, in order to study the infrared, the most powerful instrument ever developed for infrared study is the James Webb Space Telescope, which it will be controlled upstairs, just one floor above us, after it launches in 2018. About 2 minutes after that, control shift to this building. And we're all very excited, and it's a great tool for studying dusty, infrared, bright young stars. And here's a picture of me in front of the mirrors of the James Webb. So that's going to be in space, what's sitting right there. That's pretty amazing. Now, when I want to study young stars, there's one problem, which is that the telescope that I want to use is sitting in a clean room in Goddard Space Flight Center and not in space. So I had to use the current state-of-the-art in the infrared,